Batteries as electrical storage have entered the electrical industry since many years, and their development in terms of size, capacity, and efficiency has taken many leaps since then. Careful design as well as accurate monitoring of the electrical properties of a battery is crucial during the development phase. In addition, their late integration in renewable energy production, electrical vehicles, and increasingly small mobile devices has raised the bar significantly. The LMG600 achieves top accuracy and versatility in the market. It is therefore intriguing to present and investigate it as a smart battery testing system. Such a system will benefit from four key components of the LMG's core functionality: the custom menus, the script editor, the general-purpose input-output interface, and the continuous data logging and exporting capability. In this case, we will monitor a full charge and discharge cycle of a nickel-cadmium battery. But let's first shortly explain how a typical charge-discharge cycle of a NiCad battery looks like. NiCad batteries are charged with constant current while the voltage increases freely. The charging happens in a rate that is expressed as a fraction of the battery's nominal current. This is defined as the current that can fully charge the battery in 1 hour. Usually charging rates of 10 up to 100% of the nominal current are applied. Towards the end, gases are generated in the cells, which leads to a rise of pressure and temperature. At this point, the voltage starts to drop. This negative voltage drop is a reliable method to recognize the battery's fully charged state, provided the charging current is greater than 50% of the nominal. During discharging, the voltage drops gradually at a slow rate during most of the period, but quite suddenly before the battery drains out. Not controlling the battery's voltage can lead to reverse polarity of a cell and cause permanent damage to the battery. A NiCad battery test bench consists of the following basic components: the battery, in this case a 6-cell serial array, a constant current power supply, and a high power resistor used as load. 2 relays are additionally used to switch between charge, discharge, or standby modes. Another useful quantity to measure is the battery's internal impedance. This is defined as the AC component of the battery's voltage divided by the AC current flowing through it. This measurement requires a modulated battery current with a frequency, as commonly applied, at 1 kHz. To measure this, we need a signal generator in combination with an inductor and a capacitor positioned as shown in the schematic to block the AC and DC current components from flowing towards the power supply and the signal generator. Adjusting the amplitude of the AC signal, we can achieve a power factor on the battery very close to 1. The measured internal impedance is therefore almost equal to the internal resistance of the battery and can be used to calculate the joule losses. We start the test by setting up some basic settings on the power analyzer, such as the frequency synchronization source and filter. We make sure that the measured frequency complies with the modulation frequency of 1 kHz. We set the cycle time to 1 second and select the values we want to log at every cycle and export at the end of the test. For each application, the user can build their own custom menu. Therefore, one screen is enough to collectively present all the important values: voltage, current, power, internal resistance, total energy and charge, joule losses. On the same menu, we see a plot of the charge-discharge cycle as well as buttons to control the charging state and energy integration at any time. The batteries control algorithm written in the script editor runs in the background. The negative delta V and the minimum voltage detection is implemented there. Further calculations and integrations for the not directly measured values are programmed, as well as the control button actions which lead to digital outputs towards the relays. By recognizing the voltage drop during the end of the charge, the LMG600 can warn the user to stop charging, or automatically disconnect the battery from the charger, sending a signal through the GPIO interface to the charge relay. As the battery discharges, when the voltage reaches its minimum limit, the LMG600 will automatically disconnect it from the load by sending a signal to the discharge relay. Apart from that, different charging routines and scenarios can be programmed to investigate the battery's behavior under different types of stress. The described test bench looks like this. The circuit is partially implemented in this connection box, where all the external components are connected on the corresponding jacks. Here we see an overview of the measurement circuit. When the charging relay is closed, current flows from the power supply to the battery, charging it. When the discharging relay is closed, the battery is discharged through the load resistor. When a relay closes, the script makes sure that the other simultaneously opens. With both relays open, the battery is floating. As the test progresses, all the measurements are logged. At the end of the test, they can be exported to Excel or MATLAB. Smart and flexible, the LMG600 can be the core of every battery measuring application. Different types of batteries can be tested with different charging and control algorithms. No matter how challenging the application, the setup is always clear and simple. A powerful feature package that combined with top accuracy can be an indispensable tool for every battery R&D lab.